Okay, in this video we'll try running the Excel program CU Hydrograph. This does hydrograph separation, and it analyzes the hydrograph to estimate the various different terms in the water balance. So there's some instructions here, and if you need a refresher, take a look at those instructions. To start off with, go to the Data tab, and when you're first using the program, you would put data in these columns here. The hydrograph data themselves go here in a date and flow format. The date is every day, and the flow is in cubic feet per second, the average daily flow for that particular day. This column is the log of the flows, and if it's gray, and in general, don't edit any of the gray columns. In these two columns, we have precipitation data, and these are monthly precipitation data. So this is the month, and this is the precipitation amount, and the units here are in 1/100ths of an inch per month. And the reason we use those data is because if you go to this site here, this is supported by NOAA, and this has many rainfall data in units of 100ths of an inch per month. So you should be able to get access to the data and copy it in a block that looks like this. Here's the date, and then this is the month, starting with January. So if you paste the data in this green block, then the program should, when you run it, take these data, read them, and then write them into these columns here. But you need to check that because it may not work properly, and so you need to just verify that it is indeed working. If it doesn't work properly, then what you can do is paste the data here and simply go in. This is the all of the rainfall for 1979. So what you would do is copy and then paste it here and use paste special and go to transpose, and that rotates this row into a column, and then copy this and paste it right here. And if this data translator isn't working, you would just simply need to go through all of these rows and make them into columns and paste them in here. Okay, so that's the setup. In addition, you should check these numbers up here. This refers to the cell A4, so it's the starting date in your data record, and this should be the end date, or the cell that contains the end date. In this case, A4021, way down here in the A column. And what's happening here is the cell format converts these dates that you see here in a standard date format into the Julian day. And this is the format that's used internally within the program. And these numbers will come in handy if you have to reset the ranges of plots in the program, which you likely will have to do. Okay, also as part of the setup, you need to define these 4 ranges. And the way to do that is to go to Formula, Name Manager, and find the name that's shown here. So let's see, we go to Date, it's here, and Date, or Data, no, Date, let's see, yeah. Date is this range of data here. So A4 to 420. So it's basically from here down to the end. And discharge is also going to be a range variable, and it's the next column, B4 to B420. precipitation dates and precipitation values would be this column here going down to the end of the data, and precipitation values would be this column. So if you paste in data that has either more or fewer points than what's shown here, then you need to adjust these numbers here. Probably you will keep the first number the same. It'll probably be the fourth row, but you may have more rows or fewer rows than what I'm using here. And so you need to adjust this, and the reason is because the program that goes and reads these data uses these numbers, or uses these range values, to know where to get the data from. Okay, so if we have these things filled in, the data should be entered satisfactorily. And then we'll go here to the next tab, Hydrograph. And this will be the first place where we do some calculations, but we also need to use this to set the rest of the program up. For the analysis, we need to enter three different numbers. One number here in this green box is the watershed area in units of square feet. So you do whatever conversions you need to do, but it has to be in units of square feet. This is the segment time here for partitioning up the hydrograph, and something in the range of 4 or 5 days up to maybe 8, 9 days, something like that generally works. And then this is the basin constant, and there's another couple of worksheets to try to give you some ways to estimate what the basin constant should be. So if we just try doing this for the defaults, in order to run the programs and fill in these tables, we press this button, and that goes into a Visual Basic code and runs it and does the calculations and writes it out. And what we see plotted here is the discharge as a function of time, and the blue line here is the total discharge. That's what we got from the USGS website. And you see marked on here in pink, these are the minimum flows, in this case every 7 days. So we blocked off the data set into 7-day groups, and we took the minimum flow during those 7 days, and that's the pink points. And then we do a separation or a filtering using the method that's described by the Institute of Hydrology, and it gives these points here as base flow turning points. Okay, so that looks pretty good, and we also, now before we leave this page, we want to check and make sure our value of A is okay. And to do that, we can get some more data here on this page, here this basin constant page. And what this does is it allows us to get access to a couple of different types of information. This is the hydrograph here, and it's shown from 1978 to 1983 or so. This is only a portion of the record. This data set goes for 11 years, and so we only see part of it. But what we see up here in the data are places like this one, where we have a very nicely defined linear drop, linear decrease, when we plot the log of the flow rate as a function of time. So this we would interpret as a base flow recession. And these are as well, possibly. So what I've shown here is another look at the data, and instead of seeing all of the flows, these are just the turning points that are plotted. So it's just a little simpler, and we see that we have some negative slopes here that are fairly consistent. And so what we can do to estimate A, one approach, is to determine the the slope of these lines. This is log flow as a function of the time. And so this slope is going to be the exponent in a negative exponential function. And we saw in the previous video and in the notes that go with this analysis that during a base flow recession, we expect that the flow in the stream will conform to a negative exponential function of time, with a being the coefficient up in the exponent. So one thing we can do is make these fits or these fits, and then Excel allows you just to drag these over, bring them together here, just so we can basically kind of do a comparison. And so these are all really quite similar. And so what I said was, well, I'm going to assume that these lines are represented by this thin line here that is underneath the blue line. And that line gives me, there's 4.6 to 6.2. So this is a log scale. So it's a change of 1.6 log cycles over 1, 2, 3, 4 and a half months. Okay, so the slope is going to be 1.6 divided by 4.5 times 30, basically the number of days in 4.5 months. Okay, so if I base A, my recession constant, on these slopes, then I get a recession constant of 0.01 per day. Okay, so this is the master recession constant method, and it is one approach. We do a similar thing up here. Okay, well, what I found when I've tried this method out is that doing this seems to estimate a value that's a bit too big or a bit too small of a negative number. And the reason for that is that that you tend to focus on these long recessions, and there are recessions in here that are shorter that are a bit steeper and give you what I think is a more representative value. So one way to estimate what this is to go and use these plots over here. And what's shown here is the slope of 3 different data sets. And what I did was to go through and fit the data, fit all of these data with a linear regression, and I used either 3, 4, or 5 points in the regression. So I would have used, say, let's see if we can see some that are isolated. So maybe there's 3 points. They would have been fit with a line, and we get the best fit slope. And then we would go and we expand that, and we would fit it with 4 points. So we would have those 3 points plus this one. We would get a much different slope, probably a positive slope. But down here, there would be 3 points, and there would be 4 points that we would fit, and we would get a slope that would describe those 3, 4, and 5 points, and those would all be some negative slopes. So we just go through the data set and generate all these slopes using different numbers of points. And those data are plotted here and here. And we see these plots done in 2 different ways. This is the slope as a function of time, and this is the slope as a function of the probability. So let's look at this one first. What we see here is that we've got the green, which is 3 points, and the blue, which is 5 points. And there's another one that should be on here. It's hard for me to see the 4 points, but the thing to see here is that if we use these blue squares or diamonds, that the maximum absolute value or the minimum value of slope that's indicated by the blue square, the blue diamonds, is right in here. It's about 0.018. If we take a fewer number of points, we can get some even steeper slopes. But if we take fairly, if we say, well, okay, probably something in here would get the steepest number of, the steepest slopes defined by 5 points. So something in the range of 0.015 to maybe 0.018 would be a pretty good value. Now, remember when we did this calculation, we got 0.011, which is up here, and you can see that that's I don't know, reasonable, I guess, but there are quite a few of these smaller groups of points that are a bit steeper than that. So I would probably go with something in this range. We can take a look at the data here that's plotted, same data, but it's plotted a little bit differently. This is the slope, and this is the probability that A is less than this number. So if we, and again, we have different numbers of slope, or different number of points in the slope. So if we take here 0.01, so 1% chance that the slope is less than this value, then if we take 5 points, it's about 0.017, and if it's 3 points, it's 0.02 and change. Okay? So what probability is best? Well, it's really going to be up to your judgment. I'll show you the consequences, though, of having points that, or using a recession constant that is greater than these slopes. What you'll end up with is places on the interpretation that show a negative recharge. That's just the consequence of the analysis. Okay, so I think something like 0.015 to maybe 0.018, something in that range would be a good value for A. So we'll go back here. There's 0.018. Let's just change that. Say, okay, I think 0.015 is going to give me a better number. And then you want to run this page again. That does these calculations. And now we're ready to do the rest of the calculation. So skip over base and constant and go to results by day. When you get here, this will run the calculations. And what I usually do is go in here. You're going to rewrite all of these numbers here. But in order to tell that it actually is doing something, I usually erase this little block here of zeros and run it, and you'll see this thing flash a little bit. It's doing the calculations, and now you can see here it writes over these data. And so now everything, all the calculations are redone. All the data now is written in here, and we're ready to take a look and see what the results are. Okay, so let's see. What I have here are a few plots that show some of these data. Now, one thing I should point out is these plots are set up in Excel, and the ranges of these plots are entered automatically. Let's take a look at this axis. Okay, so this is a date axis, and the date, in this case, it's auto, but see these numbers here? 28800, that's the Julian day. And that, in this case, this plot is giving me what I want for a range, but what can happen when you enter your data, it'll be a different range than was used in the analysis previously, and the plot may not show any data at all because the range here doesn't move with the data necessarily. So if that's the case and you want to reset the range, just go back here to the data and use these numbers right here to reset the range of the plot, and that'll get you back on scale. So the program writes out the data to this worksheet, and we've got the precipitation, storm flow, base flow, and so on as a function of time. And this is a daily output. So this is the same time scale as the flows from the hydrograph data. And what it does, since the precipitation is monthly, you can see here it's the same precipitation for that whole month. So some of the data are plotted here, and we can see what the interpretation is. The blue, the dark blue, is the total flow. That's the data that we put in. The light blue is the base flow, and that's interpreted. We use this base flow separation technique that we just saw, and we also use an interpolation technique between the turning points that's based on the assumption in this case that the recharge between the turning points is uniform. And we also then have the recharge. This pink line here, we expand this out here. This gives us the legend here. There's the recharge. You can see it's kind of a step function. And what it's doing is, in this separation, there's a turning point here and a turning point here. And it's assuming that the recharge is uniform between those turning points. So it's kind of steppy. But you can see, well, we had this big rainfall here, probably in the mid-spring, and that caused the recharge to be this amount. And the recharge is shown over here on this scale, and it would be 0.005, and the units are feet per day. Okay, so we can see the recharge being distributed like as shown here. One of the things I should point out right here, this place, the recharge here is 0, and here the recharge is slightly negative. And this doesn't really make sense in the conceptual model that we use for this particular analysis. There really is no legit interpretation for negative recharge. If we were to make the recession constant a bit of a bigger negative number, so if we went with, say, 0.018, this line here would move up a little bit. So that's going to be one thing that you'll need to just use some judgment on. And you want to have don't want to have a lot of negative recharge, although there will be some. If you can see right here, there's this pink spike down here. That's just a few probably anomalous points, and that's okay. That seems fine. That's just an anomaly. This might be a little bit too low, although it might be just fine. There's a bit of a gray area here in the setup. Okay, so what we also have is the change in storage, and that's shown here by this brown line. And you can see here where we've got some high recharge, the change in storage is positive. Again, we are using this scale. And then down here, we have a change in storage that's negative. These places where the recharge is relatively small, or 0, the change in storage is negative. So water is being depleted from the aquifer. That's the interpretation that we get from this analysis. So really get quite a good bit of insight into what's going on in this particular aquifer. Okay, so one thing we can also do is to click on this guy, and we see that this is a plot of the data. This is the x-axis, and this is recharge uni, it's called. Well, as it turns out, there are several different types of recharge that are calculated here. There's recharge uni, recharge pulse, another recharge pulse, recharge thin. So what these things are different analyses are used to calculate the recharge, and they differ based on the assumption of how the flow or how the recharge is distributed between the turning points. So back here, when we're doing this analysis, we say there's recharge, or there's base flow here, and there's base flow here. And then between these points, we have to make some assumptions about what's going on. And so the simplest assumption is that there's recharge that is uniformly distributed across this interval. Well, I mean, that's one approach, but probably another valid assumption would be that the recharge is really associated with this pulse and rainfall, that the rainfall goes up and that pushes some of the water down and gets it into the aquifer. And so rather than being uniformly distributed between the turning points, it's really more of a pulse and perhaps associated with this peak flow. It also could be a sinusoid. So, and this is just the first half of a sinusoidal wave, and so it goes up and comes down like that. And so those different assumptions are included in the analysis, and they're given in these different columns. The different assumptions give you different values of recharge, as well as different values of base flow for the uniform, the different pulses, and the sinusoid. And we can see the consequences of those different assumptions here. This is a plot that shows some more of the data, and here the blue is reproduced. That's the hydrograph. And what we see now are the plots of recharge shown here and the plots of the base flow shown here. And we're using these different interpretations of a pulse, a peak, sinusoid, and so forth. And so let's kind of spread this out a little bit. So what you see is that the basic uniform recharge assumption is shown in the back here in dark blue. So it goes up and comes down, and it's kind of steps like this. And then these various different assumptions, the pulses are this blue here and the light blue. And so if it's all as a pulse at the beginning, then we get this medium blue. If it's a pulse that's applied at the peak rainfall, then we get a recharge that's distributed like we see here. And if it's a sinusoidal distribution, then we get this pulse or this distribution that looks like kind of looks like a sinusoid. Okay, so these are all different ways that we could interpret how recharge is applied between the turning points, and it gives us these different results. Here we can see this isolated pulse of recharge is a pretty good example. So there are different interpretations, but really, the differences are not really all that great. So in the grand scheme of things, it probably doesn't make too much difference what you assume. Up here, if we take a look at the base flow, we see some more differences. The base flow with the uniform distribution is the blue. That's what we have been using. But you can see that these two brown lines are pulse increases in the base flow, and this green line is the sinusoidal. So you can see that actually when we assume these different ways that the recharge is applied, we get some pretty different results for the base flow. And in all cases, what we're doing is interpreting or interpolating from a base flow turning point here to a base flow turning point here. So all of these functions start at this point and go to that point, but the way that they do it differs depending upon the assumption about how we think the recharge is applied. Okay, so I generally go with the uniform distributed recharge, but there may be reasons that you would want to use these other values, and so they're provided for you in these columns here, and you can use them however you want. Maybe it would be appropriate to take some averages or whatever you decide is appropriate. The data are here and available. Okay, so these are daily data. What's also helpful is to have the results averaged out by month or by year. So if we go to this page here, results by month, we see the months are shown here, and these are all of the data um, where they've been averaged every 30 days. So precipitation, ET, and then we have these different values for recharge depending upon how it's distributed, and different values for base flow, and different values for volume stored. And so we could plot these data up, the monthly averages up, and here are some results for that. These are showing, this is now really just the first, let's see, a little bit over a year of data shown just as monthly averages. And so this is just a little bit easier to digest than those daily data, but it really all depends on the application. The daily data may be useful if you need that kind of resolution. Now, all of the data are put out here as these monthly averages, and we can average the monthly averages, and this is shown here. Now, the program does all these calculations for you. It takes all the January dates and averages them and gives you results for these main components of the watershed, the water fluxes. So let's see. Yeah, okay. Probably be easier if we zoom in a little bit. Maybe that's a little too much. Okay. So the monthly averages here. Here are the results in feet per month, and I should comment about the units. The units of feet were done because the units of the data were in cubic feet per day for the flows, and so rather than convert, I kept those basic units, and and that's really the origin of why those the particular units are used. It was the convention that was established for the data. But, of course, you're welcome to convert to whatever is useful. So we also have some summary information of the data that's been calculated here, and it calculates the annual averages as well, shown here. So if you wanted to run a steady state model, for example, and you wanted to input a value for the steady state recharge, this might be a good value to use. So there's the recharge in feet per month or in feet per year. So 3/4 of a foot per year for the average recharge over these 11 years. That's what's coming out of the data. And then we also have some checks here on the volume balance. And what's shown up here is to take these different values of flux and normalize them to the precipitation. So if we took these guys here, and if you took that number and just divided by that number, then you get ET. And here, ET is 63% of precipitation, so we recognize that as a pretty typical value. And runoff and recharge are runoff is a little bit higher than recharge. Base flow and recharge are pretty similar. They're only going to be differing by the change in storage over this time period. And you can see there is a little bit of change of storage. but it's really very small compared to these. It's probably just a round off error. Um, and then finally, we have a check here where the different components are summed up, and we really are able to estimate all of the components of the watershed balance if we look at at least the main basic components for watershed, aquifer, vadose zone, and stream balances. So those components are shown here, and you do the balance, and these numbers here are the results. You can see things are added up there. And you can see in this case, to this many significant digits, we get zeros, so the balances are holding. This is really just a check that things are working right. And you should definitely check the results, because there's a lot that can go wrong if the program isn't set up right. So check and make sure that's working. And then here are some of the results plotted up, where we have the fluxes, the average fluxes as a function of time, and this is showing some dynamics in the watershed. And let's see, I mean, one of the interesting things that you can see is recharge and base flow. So if we maybe zoom in a little bit more. So recharge here is the purple stars, and it's going like that, and base flow is going like this. So what we get is both of these guys are cycling through the year. So here's about the max recharge, and then it drops, and this is about the minimum in months 4 and 5, and then it comes back up. The base flow, the discharge from the aquifer, it peaks right about here, and then it also has a minimum right about here and comes back up. So it cycles. We could see this a little bit better if we got rid of these lines and changed the scale, but I think you can see well enough these two different things that are cycling. And what's kind of interesting is that the recharge is cycling, and the base flow is cycling too, but it's lagging behind the recharge by a month or two. So the peak discharge is here, the peak recharge is about here. And so what's happening is the aquifer is receiving this recharge, it's filling up, and as it fills up, the discharge out of it is increasing, but the max discharge is lagging behind, and the min discharge, the minimum discharge is also lagging behind the minimum amount of recharge. And so that seems right if we're changing the inputs to this large aquifer system. It seems like the outputs should lag behind by some characteristic time, and in this case, for this aquifer, it seems like it's a month or so. So when you go and do the analysis for your systems, you should take a look at plots like this and try to interpret them, try to make some evaluation based on what it's telling you about the hydrology. If we, I guess, take another look at this in terms of the change in storage, we see some negative change in storage here and positive change in storage here. So what we get from that is that during this interval, this guy here is the recharge. And so the recharge is less than the base flow. So that means that you have more flow coming out as base flow than flow coming in as recharge. And the only way that that's going to happen is if you're removing water from storage, and that shows up here as this change in storage. So it's all internally consistent. This is when the water is being removed from the aquifer during in this case, spring and early summer, and then it's being replenished here in the fall. So you can get really a remarkable array of insights from the aquifer, really just from analyzing what the stream flow hydrograph is doing, and then also including precipitation